Hi guys, it's Kate, and this is the first video for week 6 of Math 23B. This week is the beginning of Module 5, and Module 5 is basically a collection of miscellaneous items, all of which are important in their own way, especially as you go into studying higher level mathematics and move into greater abstraction. For us in particular right now, we're going to take the notion of a change of basis that we've been talking about for a while, really since last semester, if you can remember that far back when we were discussing linear algebra, and start to apply it now in a more abstract setting. So the first key issue is to introduce what an abstract vector space is. Now, recall what a vector looks like. Here are our two standard basis vectors in R2. And for a minute, I want you to look at them in a different way. For most people, they see this vector and they think, okay, the first standard basis vector means 1 unit movement to the right and 0 units up. And that's great, except that to your average person, this vector right here, 1, 0, or 0, 1, really doesn't mean anything. It's just two numbers sitting next to each other. What our mind is doing is that it's sort of looking at these two components of the vector, and these two components of the vector are coefficients on the standard basis vectors. So what I want you to think about is that 1, 0 is really 1 times E1 plus 0 times E2, and that resulting sum is the total increment of change represented by this vector. Likewise, the second standard basis vector is really 0 times E1 plus 1 times E2. And you can see that any vector, no matter what it is actually coefficients, right? The components of the vector are actually the coefficients on the standard basis vectors who give a linear combination whose result, the sum of which, is the vector you're looking at. Now, unless otherwise specified, these coefficients are coefficients on standard basis vectors. But for today and for this week, we're going to say, what if our basis was not standard basis vectors? What if our basis was not even vectors at all? Consider the following. The space of polynomials of degree less than or equal to 2. They all look like this. A plus bx plus cx squared. Now a, b, and c can be non-zero or they can be 0, but this is the space of all polynomials of degree less than or equal to 2. And the thing is that every single element has coefficients on it. So we could actually use vectors to represent various polynomials. What if I had the polynomial 1 plus 2x minus 3x squared? Well, if I was talking about a basis for the space of polynomials of degree less than or equal to 2, I know that the three elements of that basis are 1, x, and x squared. Those are the three things that I need to make linear combinations with to create every single polynomial in the space. So if I was creating a vector with respect to this basis, and I was trying to create a vector that represented this particular polynomial, well, the first component would be the coefficient on 1, the second component would be the coefficient on x, and the third component would be the coefficient on x squared. I would get this vector as a result. 1, 2, negative 3. Now, of course, I'd need to know the order of the elements of this basis. That's important because the component right here is always the coefficient on that first element in the basis. The second component is the coefficient on the second element of the basis. And the third component is always the coefficient on the third element of the basis. Just like in the standard basis, where we take it as given that the standard basis vectors are E1, E2, E3. They have an order to them. And we look to that first component to always be the coefficient on E1, the second component to always be the coefficient on E2, the nth component to always be the coefficient on En. And so once we've chosen a new space, right, and a new basis to describe that space, we can start creating these vectors. They're not useful to visualize as arrows, that's why they are called abstract vectors, but they are able to encode information about particular elements in this space. For instance, in this particular example, we had the polynomials of degree less than or equal to 2, and if we used this as our particular basis, that means that we could encode this element in that space using this vector. And you might wonder, why am I even doing this? We're going to go through some examples in lecture that are really quite astonishing with what you're able to do once you start describing spaces this way and using vectors to describe elements of those spaces. Let's take a look at the axioms for an abstract vector space. First, there's the fact that there's a right additive inverse. There exists some zero element in the vector space such that for all elements in the space, if you add on 0 on the right, you will just return that element. The right additive inverse means that for every single element in the space, there's another element in the space so that if you add them together, you get the 0 element. That vector addition is commutative, right? It doesn't matter what order you add two of these abstract vectors to each other in. You're going to get the same result. And vector addition is associative, right? You can group various addition operations. Say, in a sum of 3 particular vectors, you can add the first 2 together and then add on the third, or add the second 2 together and then add on the first, and the result will be the same. The fact that the multiplicative identity 1 in F is also a multiplicative identity for vectors. Scalar multiplication is associative, that alpha times beta times an abstract vector is equal to alpha times beta times that abstract vector, and that scalar addition is distributive, and that vector addition is distributive. So very similar to when we're dealing with a non-abstract vector space. Now note that axiom 3 is actually redundant. We've noted this right here. It can actually be proved from the others, but it's conventional to include it because it's so important. But without axiom 3, we actually have a list of independent axioms, which means that no axioms can be proved as a theorem by using the others. But the one that does look like it could be provable is number 5, that we have the multiplicative identity 1 in a field is also a multiplicative identity for vectors. But note that if you modify R2 by defining what multiplication by a scalar is, saying that if we take alpha and have it act on the vector xy and have that return alpha x but 0 in the y component, we have a situation now when if alpha is equal to 1, vector axiom 5 is failed to be satisfied, but all the other ones actually are. So that shows that axiom 5 is in fact independent from the rest. We always make sure to list it. Let's scroll down here. If you leave axiom 3 on the list, commutativity of addition, then it's true that 0 is also a left identity, and that the additive inverse is also a left inverse, but remarkably both of those statements can actually be proved without using axiom 3. And that's going to be the topic for your proof 19.1. You'll have to do that the right additive inverse is also a left, the right additive identity is also a left, and then commutativity of addition are going to be the 3 proofs included in 19.1. Other rules for vectors which make sense for any underlying field are that 0 times any abstract vector gives the 0 vector, and that -1 times any abstract vector equals the additive inverse of the abstract vector. Those are not on the list of axioms because they are provable theorems, and we'll be exploring them later in the week. Some notable examples of abstract vector spaces. Note that I already mentioned polynomials, but we also have subspaces of Rn, right? That's not simply Rn itself. We've sort of already experimented with that throughout first semester. But subspaces of Rn and then displacement vectors that appear in physics. We're really going to be working mostly with polynomials this week. And the occasional trig function. As we start talking about different abstract vector spaces, you may realize that there are multiple bases that can describe a single abstract vector space. And as you may have already started to suspect, an abstract vector space can be finite dimensional, and in that case, the space will have a well-defined dimension. But there's not going to be a standard basis like there is in Rn. So that means that no matter which basis you're using, right, the number of vectors in that abstract vector space basis will be the same, regardless of which basis you are deciding to use. Note that a space may also be infinite dimensional, and an example is the space of all polynomials, whereas a finite dimensional space is like the example I gave at the start of this video, which was a space of polynomials of less than or equal to degree n. The example we discussed briefly was where n equals 2. And note that a space, when it's infinite dimensional, is not going to have a finite set of basis vectors that can span the space. Your proof 19.2 for this week will be to show that any two bases of an abstract vector space have the same number of elements. And as you might suspect, we may want to transfer from one basis to another. The key for us is to introduce a particular concrete to abstract function. Now, what does a concrete to abstract function mean? Well, if we have any finite set of vectors, v1, v2, all the way through vn, and we're using abstract vectors to describe linear combinations of these, the concrete to abstract function is basically the mental process we use to look at this particular vector. a1, a2, all the way down to an are its encoded components, and realize that this vector is an abbreviation for this linear combination. So this is something that's concrete, it's an element of Rn, but this is an element of the abstract vector space that is being represented by that vector. And so the concrete to abstract function is mostly done in our head. It's not something where you can write it down as a particular matrix or anything like that. It is the translation that you go through in your mind to take a look at this and say, okay, a1, a2, a3, a4, all the way down to an is actually equal to a1, v1 plus a2, v2 plus a3, v3, all the way down to an, vn. That's what the concrete to abstract function does. We won't be writing that down explicitly on paper. That part we will be doing mentally. Now the change of basis matrix, very similar to before. We'll have one basis for the vector space and another basis for the vector space. In this case, we call them old and new. And every new basis vector is a linear combination of the old ones, right? A basis means that it can span the space. It can describe any element in the space, including a basis vector in terms of the other basis. And so we're going to construct matrices that tell us exactly how to express the new basis in terms of the old basis. So the question here is, what is P really doing? Well, it's going to take one of these vectors, which has those, it's like an abbreviation, right? All of these encoded coefficients here that express a linear combination in the new basis, and it's going to spit out another vector that is playing the same role. All of these components are encoded coefficients for the old basis. So when we say that P expresses the new basis in terms of the old basis, it means we give it one of these new basis vectors that has the encoded coefficients that have of the appropriate linear combination, and it's going to give us the coefficients in terms of the old basis. It's going to tell us exactly what coefficients we need on which of the basis vectors in the old basis in order to represent the exact same element of this abstract vector space. Now, what is P really doing? Well, it's manipulating the concrete to abstract function, the idea of going from an element of an abstract vector space to an element of Rn that represents that element of the abstract vector space. So the very first thing that P does is it takes a vector of new coefficients and converts it to an abstract vector. And then it takes that abstract vector and spits out a vector of coefficients, but now with respect to an old basis, right? It's going from a vector that represents the coefficients with respect to the new basis to an abstract vector, and then taking the abstract vector and representing it with the coefficients with respect to the old basis. So this is the way that we can write P as a composition of both the abstract to concrete and concrete to abstract functions. We need a composition of functions there. And of course the matrix P inverse has the opposite effect. A lot of the time it's easy to write down the matrix P, but what we really care about is P inverse, because we want to go from old to new, not new to old. An interesting result is that if the old basis consists of standard basis vectors in Rn, while the new basis is a basis of eigenvectors, then the columns of P inverse are going to be able to express each standard basis vector as a linear combination of eigenvectors. Why is that? Because P inverse goes from old to new, rather than new to old. We're going to go through a lot of examples of this. The key piece of advice I have for you is make sure that you're clear about which vector space you are starting in. You know, when you're writing down a vector, those components are coefficients on basis vectors. which basis are you talking about? And then make sure that you understand, okay, the vector that I have this matrix act on is from this particular vector space, or written in terms of this particular vector space, and the vector that comes out as a result is going to be written in this vector space. Make sure that you're clear which is which. You'll have a lot of practice. It's going to seem very similar to what you did in the fall when you were doing diagonalization. And that's sort of the key point, except now we're dealing with abstract vectors rather than just plain old elements of Rn. Now, what if you want to do more than just translate from one basis to another? Granted, we'll be doing a lot of that because that's very useful, especially when it comes to sort of swapping between spaces described by various trigonometric functions. In fact, you're going to be able to find some interesting trig identities using this skill. But what if you're trying to find a linear transformations effect? Well, if you have two abstract vector spaces, then a linear transformation T can't be uniquely identified with a matrix because you have two different ways of describing every single element in these vector spaces. So, but if you're on a quest for trying to write down T as a matrix, right, we want a matrix T that represents this linear transformation relative to bases in V and W, and it's going to be a composition of three separate transformations, right? Not only are we saying, again, big picture, not only are we saying I want to go from talking about elements with respect to the V basis to elements with respect to the W basis, right? That nothing is actually changing about the element in that process, just how we describe it, the linear combination that we use to describe it. In this particular case, we're going to start with this operation, right? That's a concrete to abstract. That means that it's going to take an element of Rn and convert it to an abstract vector with respect to the vector space V. Then we're going to apply the linear transformation T. That's going to convert this to an abstract vector with respect to the vector space W. And then this is going to go from abstract to concrete, which is going to convert this abstract vector in W to a vector in Rm. And so there's this three-piece composition right here that is the overall matrix representation of the linear transformation T, which first acts on a vector written in terms of the abstract vector space V, and its output is going to be an abstract vector written with respect to the vector space W. And in fact, if you're able to figure out what the matrix representation of T is in terms of the old bases in V and W, then you can also figure out what the matrix representation of T is with respect to new bases for vector space V and vector space W. Note that vector space V is the vector space of the domain, and vector space W is the vector space of the image. But you can go ahead and find T with respect to any new basis by basically constructing this composition. First, we have this change of basis, where we are going from the new vector space to the old vector space, just how to describe each of the old basis vectors with respect to the new basis vectors. Then we implement the linear transformation T here, which will take us from the domain, vector space V, to the codomain, or image, vector space W. And then here, this is P inverse of the transformation that maps from new to old. So this is going from old to new, but in terms of the W bases. So you can basically describe these vector spaces V and W however you like, as long as you know one version of the linear transformation, the matrix representation of the linear transformation for T, and how it maps from V to W. Then, as long as you know how to move between various descriptions of vector space V, various bases of vector space V and vector space W, you can use composition and matrix multiplication here to reconstruct the matrix representation of that linear transformation with respect to any pair of bases that describe the domain and the codomain. This is very similar to dealing with our concrete vectors in the standard basis and the eigenbasis that we worked with back in September. Try to draw as many parallels to that as you can. It will go a long way for you, but we will be doing lots of examples in the classroom.